All right, so chapter 3 is going to focus on water's role in living things. We talked a little bit about this back in chapter 2 about how water has polar covalent bonds. You have a super electronegative atom oxygen that's bonded to not nearly as electronegative hydrogen atoms. So that's going to cause an unequal sharing of electrons within the molecule's covalent bonds. Water is able to act as the biological medium on Earth because of that polar nature that is present in water molecules. Living things require water more than anything else. So your cells not only are immersed in water within them, but they themselves are surrounded by water. And it's that reason that Earth has been such a favorable location for living things to be able to survive and reproduce. Water molecules, because of their polar covalent bonds, are able to hydrogen bond with one another, and that also is going to play a pretty critical role in some of the characteristics that we're going to look at with water in this chapter. So 4 emergent properties that we're going to focus on: its cohesiveness, its ability to moderate temperatures, that it can expand when it's freezing, and how it's able to function as a solvent for so many different types of substances. So the first one we're going to talk about is cohesion and corresponding adhesion, as well as surface tension. So cohesion is what's going to take place when the hydrogen bonds hold the same type of molecules together, in this case water, and that's how water is able to go against gravity and move up in plants. Adhesion is when there is an attraction between those intermolecular forces between different substances, and we see that as well with water and moving up plant cell walls. Surface tension is representative of cohesion because, again, the water molecules, the hydrogen bonds are holding them together, those connections between the adjacent molecules, and all of those would have to be broken for the surface tension to be broken as well. So the next property we're going to talk about is how water is able to moderate temperatures. Water will take in heat from warmer air and it'll release heat to cooler air. And it's able to do that without really changing temperature drastically. We talked about potential energy in chapter 2. Kinetic energy is going to be your motion energy, and that's going to kind of correspond to heat. Heat is the amount of kinetic energy due to the motion of your particular molecules, and we typically will represent this in either calories or joules. And if we are talking about it in terms of calories, 1 is equal to 4.184 joules. You cannot measure heat. You can calculate heat changes by looking at temperature changes or by looking at what type of phase change is occurring within a substance. Temperature is something we can measure with a temperature sensor or a thermometer, and it's going to get an estimate of the heat's intensity due to the average motion of our molecules, and we typically are going to look at this in Celsius. If you are dealing with it in Kelvin, remember that Kelvin is a calculated value. So why is water able to absorb large amounts of heat and release large amounts of heat without having drastic changes in temperature, aka what happens with our oceans both in the spring and in the fall? It has a lot to do with water-specific heat, and this is going to all come back to hydrogen bonding. Specific heat, again, is the amount of heat it takes to warm up a gram of that particular substance by 1 degree Celsius. And water-specific heat is super high compared to metals and other substances. Why is it such a large value? Why does it absorb so much heat or release so much heat before changing temperature? It's because you have to either break the hydrogen bonds holding the water molecules together when heat is being absorbed. So some of the energy has to be used to break those connections before the temperature can change. You also have to form hydrogen bonds in order for heat to be released. So because of the hydrogen bonds that are present in water, you're going to have a much larger specific heat value because of the strength of those connections that has to be broken. And due to that, Water's temperature does not vary nearly as rapidly as some other substances. Perhaps metal seats might come to mind, and that allows living things to be able to survive in temperatures that you would not normally think would be possible because the water's temperature is moderating compared to the atmospheric temperature. Another characteristic we're going to talk about is evaporative cooling. So evaporation is going from a liquid to a gas. It can occur at any temperature. If it is occurring at its boiling point, we can determine that by looking at its heat of vaporization. We can determine how much heat has to be absorbed to change from a liquid to a gas or how much heat has to be released. When a liquid is undergoing evaporation, it's going to take energy in to be able to escape and become a gas. And that's going to cause the surface of the liquid that remains to be a little bit cooler. It's taking heat away from that surface. As it takes heat away from that surface, it helps to stabilize temperatures in areas that are going to be closer to that water. And so that's why you see here in this particular map that the temperatures are much cooler as you're closer to the ocean because you have that evaporative cooling process that's able to take place. And as you move further away from the ocean and you don't have that body of water to help to moderate temperatures, we see the temperatures start to increase fairly rapidly. Another property we're going to talk about is water's density, both in the solid and the liquid state, why water can float in the solid state on top of liquid water. And it's able to do this yet again because of hydrogen bonds. When water is going through that freezing process, it's going to get down to about 4 degrees, and that's where you're going to see its biggest density. At that point, it starts going through that freezing process, but there are still hydrogen bonds present in those water molecules. Those hydrogen bonds, because they haven't been broken, are going to cause the water molecules to be able to spread out more. And because you have less mass and the same amount of volume, the solid state is going to be less dense than the liquid state. That's a really critical characteristic for water, especially with organisms who can only survive in aquatic environments. The ice is not going to sink to the bottom, and if that was the case, if it all completely froze, then those living things would not be able to survive. The last property we're going to talk about is water's ability to act as a solvent for a wide variety of substances. Quick review, solution is your homogeneous mixture. Your solvent is what is actually doing the dissolving. Solute is what is being dissolved. And the aqueous solution is the solute and solvent combined. Because of water's polarity and its ability to form the hydrogen bonds, it's able to take apart the ions in an ionic compound, surround them with a shell of water molecules. The cation gets surrounded by the negative oxygens in water and the partially negative charged oxygen atoms in water, and the anion is surrounded by the partially positive hydrogen atoms that make up water molecules. But water is not just capable of dissolving ionic compounds, it can dissolve molecular substances, ones made of nonmetals, that just happen to have polar aspects to them, such as proteins, if they have ionic and polar regions, but you can also have something like sugar is able to dissolve in water because sugar has components to it that have a polar nature, and that will allow the water to interact with it. We'll spend more time on membranes in our next unit, but hydrophilic and hydrophobic substances are ones that are going to have a relationship with water. Hydrophilic is when there is an affinity for it, totally fine being in the presence of water. Hydrophobic is when you don't have an affinity. We talked a little bit the first day of class about how COVID has that lipid layer surrounding it made of carbons and hydrogens. And because of that, its hydrophobic nature, water is not going to be sufficient to help to disturb it. You need something else that's going to be able to mix in with it and break up that membrane. So when you get substances on your hands that are greasy and oily, you want soap or some other detergent to get in there so that they can help to break the connections that are present. In the picture I'm showing you right here of a cell membrane, you can see that you have the tails that are the hydrophobic components that are facing inwards away from the hydrophilic side outside of the cell. Remember, we said that water is basically making up the surrounding of your cell, and it's also making up the cytoplasm that's present in your cell. So the components that are standing towards the watery side, the hydrophilic nature, are going to be charged particles that are going to be totally capable of interacting with water because they have an affinity for it. And then the last term I wanted to touch on was colloids. A suspension of particles, so not completely dissolved, but it has the appearance of being dissolved in a liquid. Milk would be an example of a colloid. So we will spend some time looking at concentration because that's going to play a role, especially when we get into osmosis a little bit later on. The majority of the biochemical reactions take place in water, especially in our bodies. The chemical reactions that do take place are going to depend on how those molecules are colliding with one another. And if you have greater amounts of particles present, that's going to increase the potential number of collisions and help to speed along that process. Molecular mass is the same as molar mass. It's the mass of all the atoms making up your particular substance. And again, that's equivalent to 1 mole of that particular substance. And then if you wanted to look at the amount, the number of molecules present, that would be Avogadro's number, 6.02 times 10 to the 23rd. So if we know that 1 mole of water is 18.02 grams, we know that 1 mole of water also consists of 6.02 times 10 to the 23rd molecules. And the Dalton term that I talked about earlier on is this representative of the same amount as the molecules. So it would also be equivalent to 6.02 times 10 to the 23rd Daltons. Molarity is looking at a solution, not just looking at the amount of a pure substance, but looking at a homogeneous mixture. How many moles of your solute are dissolved per liter of the solution that's making up your aqueous solution. The last thing we're going to talk about are acids and bases and how they're going to play a role with living organisms. Acids have the ability to donate a proton, typically in the form of a hydrogen atom, and bases have the ability to accept that proton. So if you have 2 water molecules that are connected to one another via a hydrogen bond, again, that is not a connection that makes up the molecule, but a connection between adjacent molecules. That hydrogen bond that forms can actually result in a hydrogen shifting and making hydronium ions, which is what's going to happen when a hydrogen gets donated. And it's going to leave behind a hydroxide ion. And that will be what's left of the original acid. The hydronium will be what now is present from the original form of base. H plus and H3O plus are equivalent things, so you can talk about those two interchangeably. And you see a picture down below. So you've got 2 water molecules. Water is considered to be an amphiprotic substance. It can act as both an acid and as a base. And that's what you're seeing in the picture below, because that's the only way you could get both the H3O plus and the OH minus. So this is an equilibrium process where you will eventually reach the point where the rate at which the reactants are being consumed to form products and the rate at which the products are being broken down to reform the reactants are going to be equivalent. This has actually got the equilibrium value for this reaction is pretty small because not a lot of the water molecules are going to go through this process. But the amount that do is going to play a role with your pH scale. So, as I said before, the amount of dissociation that you have for water is going to be pretty small, but because that dissociation factor is going to cause, if you have a shift, it's going to change your solution from being neutral to acidic or basic, it can have a pretty significant impact on your cell's chemistry. So in pure water, you have equal amounts of hydrogen and hydroxide. And so that's when you have a pH of 7 that you're neutral. If you have more hydrogen ions being added in the form of acids, or if you have more hydroxide ions being added, that's going to cause your pH to shift, and that can cause substantial changes with how your enzymes work and other aspects within your cell. So below 7, you're acidic, above 7, you're basic, at 7, you're neutral. When you're acidic, you're going to have more hydrogen ions present than hydroxide. When you're basic, you're going to have more hydroxide ions present than you're going to have hydrogens. In general, biological fluids tend to have a pH pretty close to neutral, anywhere from like that 6 to 8 range. If you wanted to calculate a pH value, you can use the concentrations of hydrogen and hydroxide to be able to do that. At 25 degrees Celsius, this is how we get the pH scale of 0 to 14. The product of hydrogen and hydroxide is going to be equal to 10 to the negative 14th. If I wanted to find pH, I can take the negative log of that hydrogen concentration. Remember, hydrogen and H3O plus are the same things. And by doing that, I can find the actual value for the pH of my solution. If the exponent for your hydrogen or hydroxide concentration changes by a factor of 1, your pH is going to change as well. So, I'm sorry, I should have said a factor of 10. So let's say the hydrogen had been 10 to the negative 6, then your pH would now be a value of 6. So it would be 1/10. The pH of 7 would be 1/10 the size, concentration size of the pH of 7. Here is just some everyday examples of acids and bases. And you can see in the pictures on the far left, in the acidic solution, way more hydrogens. In the basic solution, way more hydroxides. In the neutral solution, you have roughly the same for both. Buffers are what help our cells and help our body to be able to maintain pH. They are substances that are capable of minimizing additions of hydrogen ions or hydroxide ions. They are typically made from a weak acid and its conjugate base, or a weak base and its conjugate acid. So they have to have something in common. If you look at the picture on the right, you see how you have HA and A minus. So they both have the A in common, and they need to differ by a proton. So they need to be able to go back and forth. So HA could give up its proton and make A minus. A minus could accept the proton and make HA. So they've got to be able to go backwards and forwards by the addition of hydrogen or hydroxide ions. Acidification also is going to play a role looking at things more on a global scale. We produce large amounts of carbon dioxide by burning fossil fuels, and the carbon dioxide that we generate is absorbed in part by the oceans. When it's absorbed by the ocean, because there's lots and lots of water present, it's going to form a weak acid. That's how we get this, what's called ocean acidification. When we make that weak acid, it's going to be able to dissociate into carbonate ions, which then can react with calcium that's present from shells and other organisms and help to start to break down corals. And we're seeing that a lot now. I know off of Australia, and want to say, oh, bear with me. I want to say off of Hawaii, but you may want to double check that one. Anyway, where these corals are, we're seeing much smaller amounts of coral because of this increase in acidity within the ocean due to the carbon dioxide that is being consumed at all-time high levels. Another issue we run into is acid precipitation. When we burn fossil fuels, we also generate sulfur oxides and nitrogen oxides. These non-metal oxides, just like we saw previously with CO2, are able to make acids. We saw how some of the CO2 is able to fall into the ocean and cause that to become acidic. Well, the sulfur dioxide and sulfur oxide and nitrogen oxides can react with a water vapor, and they will then have the opportunity to fall back down to the earth and be absorbed by the soil as it's precipitated out in the form of rain or sleet or snow or hail. So acid precipitation, when that is generated and it's coming back down from our atmosphere to our ground, is going to have a pH less of 5.2, and that can have significant impacts with our soil chemistry. It can also affect our lakes and our streams.